some reason you have a valid reason why you're not going to be here, please let me know. I do have a way to convey the information to you. I want everybody to have a chance, but you have to at least be responsible enough to let me know, hey, I have something going on that day, I'm not going to be in class. I will give you the information. If something happens that day, you wake up with sniffles, just let me know, it's fine. Watch out for emails also the Wednesday before that with your lab practical start time, as we talked about last time. We split the group of students from the lab into 2 groups to lower the stress for you and make it easier for the TA and their helper to do things that help you through the practical. Therefore, either you'll be starting at the beginning of your lab time, when you normally start, or you'll be starting an hour and a half later. If you have a preference to starting in the first group or the second group, please let me know by, say Tuesday the 18th at night, because I won't be sending emails out to the 19th. Okay, so I'll give you some time, take away your schedules. Hey, I could get a couple extra hours in at work if I was in group 1 or something like that. So just let me know, it's not a big deal. I do tend to put ARC students in group 2, but that doesn't mean you have to be in group 2. If you want to be in group 1, that's fine, just let me know. We know we have a quiz on Friday. Hopefully you saw yesterday that the bullet list went up. So you will have to review the rules for quantum numbers, meaning what are the allowed values. Why is that not on? Sorry, I just noticed that. Sorry, you can't see, they can see it over there. The one time they can see things that everybody else couldn't. Sorry about that. We'll let that come up so everybody else can see it. Come on. There we go. Those what values of n are allowed, how is L connected to n, and the allowed values for L, the same for m sub L and then n sub S, along with providing for a complete, not noble gas electronic configuration, including anomalies such as we saw with chromium. The ones we looked at were not chromium. We looked at molybdenum and silver. Well, think about chromium and copper right above them. Remember, if you come across a D4 or a D9, you take one from the S and you put it in the D to get the ground state electron configuration. Also, make sure that we didn't discuss those in lecture. Manganese, I have to fix that. We didn't do manganese. Manganese on the brain. Also, make sure you hear the terms ferromagnetic and diamagnetic. And I will fix that manganese reference because that was not a weird one. Orbital diagrams, make sure you can produce an orbital diagram if needed. And also writing a set of quantum numbers for a specific electron in an electron configuration. And then be able to produce a noble gas core electron configuration for an ion, such as a transition metal. Any questions besides my one oops that I will fix? Good? Alright, so sorry about the oops. I'll probably resend it so everybody gets it again. Any questions at all? Get out of there before I forget. We are going to be starting our periodic trends today, and I wanted to start off with just a view of what we're going to be going through. So as far as our trends, we have quite a few of them. We have effective nuclear charge, which is where we'll be starting. From that, we'll be able to tell what's going on with our other trends. We'll then have atomic size, and subset in there is ionic size. We have ionization energy and electron affinity in Chapter 8. You may be thinking, what about electronegativity? That will not be exam 3 material. That is actually located in Chapter 9. We're not forgetting about it, though. We're just going to wait until we get there to discuss electronegativity. Any questions? Okay, so our slide says, or asks, do all electrons feel the same nuclear charge? We're at number 18, page 248. And if it was yes, then why would we be talking about this? So, no, they do not all experience the same nuclear charge, meaning they're not interacting with the same amount of positive charge coming from the nucleus. We're asked to think about hydrogen and lithium. Think about this a little bit further. You have a little table. So I have put a Bohr diagram of hydrogen and lithium up on the screen. Remember, it's not really accurate to dot electrons. However, we just do it to help our understanding. So the nuclear charge is in the nucleus there. So hydrogen has 1 proton, so +1. Lithium has 3 protons, so +3. Number of electrons total. Hydrogen has 1, lithium has 3, but on your table they're asking for core versus valence. I want to review those terms as well. So remember, a core electron electrons are the electrons that are not in the highest energy level. Bless you. So for hydrogen, there is only one energy level, so that's not a core. But in lithium, we have two, and we have two electrons that are not in the highest energy level. Therefore, lithium has two core, whereas hydrogen has none. Therefore, the other electron has to be valence. Valence electrons are the electrons that are in the highest energy level. So hopefully in our Bohr diagram it's very easy to see. Hydrogen only has one orbit or energy level, so therefore that would be a valence, that electron. In lithium, that would be the energy level that's furthest from the nucleus, so that would be the single electron with that double-headed arrow going to it. Good? When we think about those nuclear charges, we're now asking ourselves, are all the electrons in hydrogen, the electron, feeling the same nuclear charge, or there's only one there? But what about in lithium? We have two electrons that are closer to the nucleus and one that's farther away. And we did talk about shielding a little bit in chapter 7, when it gave us that kind of messed up sequence of sublevels. Remember, shielding is where core electrons, or electrons closer to the nucleus, reduce the effect of the nuclear charge on the valence electrons and electrons further away from the nucleus. So use your figure of lithium to show this using the core electrons to shield part of the nuclear charge. I use the green fuzz, a green haze. The electrons in our Bohr diagram are constantly orbiting the nucleus, but in the modern model, they're in a sphere volume of space that they could be, but they are still closer to the nucleus. Negative kind of cancels out a positive. Therefore, our electron that's outside that green haze, our valence electron, is not going to be interacting with as much positive charge. We term that, sorry, I forgot about that, we term that an effective nuclear charge. So our effective nuclear charge would be the amount of positive charge that the valence electron is interacting with. So we do have an easy way to calculate this. There's more than one way, but first just let me, I know you haven't typed it out, but helps me to write it because it slows me down for one thing. Effective nuclear charge. And I'm not going to phrase it the way the textbook has it because you have that typed for you. I like to say the leftover nuclear charge after the number of core electrons has been taken into account, because core electrons are canceling out some of that positive charge. The screen. I see a little messy. We'll fix that. Effective nuclear charge, ZeFF, equals Z, our nuclear charge, minus the number of core electrons. Again, we'll see another way we can calculate that in just a little bit. This is the simplest way to think about it. Are there any questions? Yes. Oh. Sorry. Plus, this is zoomed in a little bit too much. I won't unzoom. My last sentence, Sarah, this definition. Okay, I see your hand out there. Effective nuclear charge, leftover positive charge from the nucleus after the number of core electrons has been taken into account. Okay, we subtract out the number of core electrons. So, effective nuclear charge equals Z minus the number of core electrons. Yes, yeah. Okay. That happens sometimes when you're thinking about asking a question, sometimes the answer pops in your head. Anybody else? Kind of waiting for a common question. Where does Z come from? We're getting close to the end of the semester. I'd like to sprinkle in a little review as we go. If we reach questions? Has that brought up anything else? So we're going to think about this effective nuclear charge and how it's going to vary, as you can see, number 21, across a period. And the next page, we're going to think of how it varies going up and down a group. I forgot to put that in. That was a reminder to me to say, oh, now look, the valence electron in both of these different atoms, a different number of protons, is really interacting the same amount of positive charge. The core electrons in the lithium cancel out some of that positive. Sorry for forgetting about my click. So here is our table going across a period. We're going from sodium over to chlorine. Z, again, for your top row, is just going to be the number of protons. We know that each proton has a positive charge. So we're going from 11 to 17 for our atomic numbers. The core electrons are the same because we're in the same period. As you go from one box to the next, what you're doing is adding a valence electron. So when we do the subtraction per our equation, effective nuclear charge equals Z minus the number of core, we end up seeing a trend as we go from left to right across the periodic table. I like to draw these as box trends. So that's a Z effective. Make sure I'm, okay, there we go. And so as we're going from left to right across the period, we have an increase in our effective nuclear charge. I always draw my arrows in increasing fashion. You like to move decreasing fashion, perfectly fine. Just make sure you know what you're looking at. Any questions? We're now going to look at a slightly different way of calculating the effective, yes?
So EFF is really just the number of valence electrons for that specific element?
In this case, yes, because we're subtracting off the core.
Yeah.
Okay? Because if it's an atom, the protons equal electrons. Okay? But we're going to look at a more the scientific way of doing this. Each core electron isn't the same. The amount of shielding effect depends on where the core electron is as well and what type of orbital it's in. And therefore, we can experimentally determine shielding factors. It's noted by the sigma that is in your table in number 22. So I kept our old table from the previous page, so you wouldn't have to go back and forth and flipping. So the sigma factor is experimentally determined. It's not just canceling out core electrons. We can see here that the shielding effect is actually increasing as we go from left to right across the periodic table, whereas in the simple calculation, it's staying the same at 10. Again, it depends on where the electrons are and what types of orbitals they're in. When we do the subtraction, though, we still see the same trend, although we don't see the same numbers. So referencing the question before, yes, in the simple calculation, it is equal to the number of valence, but when we think about an actual experimentally method of doing this, it's not equal to a number of whole electrons. Actually, how much are they actually shielded? You don't have to understand really where sigma comes from. And if it wasn't for something that's coming up, I wouldn't even mention sigma. Here it gives us the same trend, so we didn't really need to bring it up. But when we're looking at our group trend going up and down, there is going to be a difference, whether we do it in the simple calculation or if we use shielding factors. The numbers are important. As you go from left to right across a period, the effective nuclear charge is increasing, meaning the valence electrons are feeling more positive charge. Yes?
So sigma is not equal to this number?
Not really, because it gave us the same trend if we did the simple calculation. Right? We saw an increase. Anybody else? As you can see in 23, we're now going to look down a group, and you can see you have a table that has core electrons in there, and then you have a subsection of the table underneath that has the sigma shielding factor in there. So this is the table I'm referring to. So lithium down to francium, down group 1. Our core electrons are going to be changing now because we're going down a group, meaning each element we go down is in a different period. So for our simple calculation, we end up seeing no trend. The effective nuclear charge looks like it's constant going down the group. Which is the reason why we had to bring up sigma. The only reason why I had to bring up sigma is because the simple calculation doesn't give us an answer. If we now include subtraction of the sigma values from the nuclear charge, for example, 3 minus 1.7 going down for lithium, now we actually see a trend. We have lower shielding higher up in the group, and the shielding increases as we go down. Therefore, as we go down a group, our effective nuclear charge is increasing. Again, the actual values are important. It's just low at the top, higher as you go down. Any questions?
So going down is increasing the protection against the feeling of the positive charge. Is that correct?
The valence electron is feeling more of that leftover positive charge as you go down. Yes.
Oh, it's feeling more.
Yes. The effective nuclear charge is basically the positive charge valence electrons feeling. They do have in 24 place for what is the periodic trend for effective nuclear charge. I like the box diagram because they're nice and simple. It's kind of like when we were doing chapter 6 and E, having a box with an arrow going in or out was nice and simple. This, of course, is from our textbook, margin figure, page 259. Notice there, even the author is only focusing on the representative elements, the gray areas. Transition metals don't like to follow the trends. We saw that with valence electrons even the other day. How do you think this might affect the size of the atom? If in valence electrons, the electrons outside, are feeling more positive charge, wouldn't you expect them to be more attracted to the nucleus and maybe get pulled in? Let's see what the effects are. So how does this affect the size of atoms? This is for number 25. My answer I wrote, we'll see. Let's see. So I don't have a direct answer, but we do have to make sure we understand how the size of atoms is determined experimentally, just so you kind of understand what the numbers are telling us. If we have a monoatomic species, what we do is we first vaporize the sample, and we put it in a vacuum chamber with some kind of solid surface to basically let it condense onto. Then we take an atomic force spectroscopy needle and basically trace out a topographical map of that surface. We end up seeing things like this that imply, oh, there's circles underneath there. And we measure from midpoint to midpoint. And then we just cut that measurement in half. So we report a radius, 1/2 just to the centers of the atoms. If it's a diatomic species, we can still get that to absorb onto a solid surface, but then we know that the diatomic is fused together already, so we just take one of them, measure from midpoint to midpoint, and then cut that in half to report a radius. Are there any questions on that? Although that's not something to be tested on. I had students ask the questions so often that I had the author insert that one bullet point so I could put a slide and students would get confused because there's nothing for me to write somewhere. So, we have this table, which is on the top of the next page, page 250. We have the effective nuclear charges that came from our sigma values. Just notice there's decimal places. It's not whole numbers. It's not just the number of valence. We are noting the number of valence electrons that are there. Do we think that chlorine or sodium will be bigger? Any ideas? Not sure? There's the trend. And by size, we're thinking about that radius. So as we are going across a period, we need to go from right to left to have increasing. Hopefully that makes sense. We have higher effective nuclear charges on the right-hand side. Therefore, the valence electrons in chlorine are being more attracted to the nucleus. They get drawn closer. Remember, they're existing in volumes of space. They are able to move around that volume of space. It's not just on an orbit like Bohr's idea. We have lower effective nuclear charges on the other side. Therefore, sodium means we have bigger atoms, where we have a lower effective nuclear charge, and smaller atoms, where we have a high effective nuclear charge. To confirm this, I've included some values for our atomic sizes. Any questions? What do you think is going to happen when we go up or down a group? Do you think the bottom of the group is going to have bigger or smaller atoms? I heard bigger? Probably because you're remembering something? Some might be thinking, huh? If these are opposite, why wouldn't these arrows be opposite? People who said bigger at the bottom are correct. Bless you. We have our effective nuclear charges, including our shielding subtraction in the table in number 27. And then we have our valence electrons noted, one for each of those, because we're all in group 1. The trend is the opposite of what you think. It's not the opposite for the group trend. It is the opposite for the period trend. By period trend, I just mean looking across a period. As we have higher effective nuclear charge, we have smaller sizes. For the group trend, this is obviously not the case. We have high effective nuclear charges at the bottom of the group. We also have bigger atoms at the bottom of the group. Anybody have any ideas what's causing them to be bigger? What's that? I think I heard right, I'm not sure. What's that? Where'd it go from? More core electrons? What do you think is going to determine the size of the atom? Like how big out that circle or that sphere goes? What's on the outside, right? In francium, where are we putting that valence electron in the configuration? Into the 7th energy level. Way far out, right? In lithium, we're putting the valence electron into the 2nd energy level. As N increases, the size increases. You're getting there. As N increases, size increases. Meaning, yes, we have a high effective nuclear charge for francium. It might even be bigger if it wasn't for that. Meaning that effective nuclear charge is probably pulling the valence electron in a little bit. But simply because the energy level is so much bigger, it ends up being a bigger atom. Although it's really hard to measure francium, every semester I try to look up the newest things for francium, and nobody has yet agreed on the measurements. So therefore, I've included the others, because I didn't want to just make up a number or take a number from one source, whereas another source is different by like hundreds of picometers. It's not different by a little bit. Any questions? The next slide is just, I think, a picture from our textbook. Yeah, there we go. That's where I got the numbers from. Notice our textbook author ended as the 6th period. He did not want to put francium on there either. I prefer the box trend. Simpler, to the point. Any questions came up before we continue to our next trend? We can see kind of where we're going if we look at number 29 as ionic, N-ionic radius is the radius of a certain cation or anion. When ions are formed, will effective nuclear charge change? No. It's all about the shielding effect of the core electrons. When we're making simple atoms, ions, from representative elements, we're adding and removing valence. Don't think about the transition metals because they don't follow the rules. So if we go from lithium to lithium plus, we're removing a valence electron. What we see in terms of the size is where the core is extended to. That valence electron added so much more size. When we go from fluorine to fluoride, we're adding a valence electron, which actually actually it causes the size to get a little bigger. Again, when cations are formed, what changes? The number of valence and the size goes down. When anions are formed, what changes? The number of valence and the size goes up. This is one of the few times you'll see the word always in science. Cation is always smaller than the atom from which it was formed, and an anion is always larger from the atom from which it was formed. I do have another view that you don't have a bullet point for. But some students are very picture-oriented, and other students are more mathematical-oriented, so I included some graphs from our textbook. It's telling us the same thing. So the graph on the left-hand side, our atoms are plotted with the blue line. The cations are all smaller. On the right-hand side, unfortunately, the author decided to plot the atoms with the red line. It's confusing. And the anions are all larger. Meaning, for your ionic size, if you think about how cations and anions are acting differently, you kind of have to treat them differently. So we know that anions are formed from nonmetals. I like to just put a little box here. And as we see here, as we go down the group, the size is increasing, just like our atomic size trend. As we go across, let's say from fluoride to nitride, the size is increasing, just like our atomic size trend. For the cations, the same thing is really happening. Now, can't really look at the transition metals. You can see there's some weird things going on there, but if you just look at the first two groups, beryllium 2+, the lithium plus, size is increasing. Down each group, size is increasing. However, if you laid the atomic size trend over the entire periodic table, you could get things wrong, right? Because size increases and then decreases and then increases again. Meaning the reason why I broke this apart is you can use the atomic size trend for ionic size, but you have to look at anions and cations separately. Any questions? Good? We have, I'm looking for what page am I on? 251. I wasn't on the right page, sorry. Here we have a sequence of ions that are not all the same type of charge, meaning we have cations mixed with anions. Again, if you laid the atomic size trend over the entire periodic table, you might get it wrong, because you might forget about that sudden change in sizes between our anions or cations. Our Z again is our is our regular nuclear charge, or just the number of protons. I purposely have two arrows there to hopefully remind students to sort them separately. However, cations are going to be smaller than anions. So that's why I have increasing across from aluminum cation to the sodium cation, break, and then increasing again from fluoride to nitride. As far as the sizes, I took them from that prior image from our textbook. Some students like to see the numbers. You don't need to know the numbers, so please don't think you have to worry about the numbers. Is there something else we can see about this? It's also noted in bullet point D. These ions are all isoelectronic, meaning they have the same electron configuration. What noble gas are these guys isoelectronic with? Easiest way to see that is what's next to fluoride, right? Because fluoride adds one electron. When it's next to fluorine, it would be neon. Meaning these are all isoelectronic with neon, meaning they have the same electron configuration, the same number of electrons. So what's really causing the size difference for an isoelectronic species? Reason why we have the row over the number of protons there. As we have fewer protons for the same number of electrons, it's bigger. As we have more protons, aluminum 3+, for the same number of electrons, it's smaller. Isoelectronic series as the numbers of protons increases, size decreases. Or you could say as the number of protons decreases, size increases, whichever way you prefer. I also have a nice easy way of remembering it. Whatever gained the most is the biggest. Nitride gained 3 electrons. It gained the most. It is the biggest. Whatever lost the most is the smallest. Aluminum's a 3+. It lost 3 electrons. The most. It is the smallest. Or you can do the sorting with this. More than one way. We all think differently. Are there any questions? We're going to be moving on to a slight, well, not slightly, we were talking size, so a different idea, but still same topic in general, periodic trends. Any last minute questions before we move on? Yes?
It says isoelectronic. What is the
Oh, a series?
series?
Sorry, I'm being really messy today for some reason.
No, it's okay.
I've got a migraine, it doesn't help with my writing. Anybody else? Oh, we have a group going by. I like to wave to groups. The tours. Okay, our next topic is ionization energy. As we can see in number 30, we're going to define this in a couple different ways. We have it with words on our piece of paper. The minimum energy in kilojoules per mole required to remove an electron from a gaseous atom in its ground state. If we wanted to think about that symbolically, yes, we're making a cat eye. The abbreviation for ionization energy is IE. So we're going from X to X plus an electron, and technically gases. Notice it is an endothermic process, and the ionization energy is greater than 0. It is the minimum energy in kilojoules per mole required, so therefore it is endothermic. Always. Think about it. The electrons are attracted to the nucleus. To remove those electrons, you have to pull them off. You have to do work, or use energy to get them out of their orbital. So again, for bullet point A, yes, it is always positive. It's energy that's required to overcome attractive forces. We are going to do things a little out of order. They asked us for the periodic trend next. So there it is from our textbook, and I'm going to draw a box trend. And then we're going to make sure we understand the period versus the group trend. When we look at the slide, we can see we are increasing from left to right across a period. And we can see that we're also increasing up a group. The period trend has to do with the effective nuclear charge. As our effective nuclear charge is increasing, we are going to need more energy to remove the electron because it's more attracted to the nucleus. Increasing the effective, we're increasing the energy needed to remove that electron. The group trend requires a little more information. If we think about Coulomb's law, electrostatic, I'm going to first describe it. Electrostatic attraction is equal to a constant times charges, positive and negative, divided by the distance between. And let's just define everything here. So K is simply a positive constant. You don't need to know the number, because you're not going to actually calculate. Q plus equals positive charge. balance is staying constant, if you put a bigger number in the numerator, I forgot to define E. You get more attraction. E is electrostatic attraction. I can't believe I forgot that. Simply the attraction between the opposite charges. So I'll go back, rewind. If we increase the effective nuclear charge, we're increasing Q plus. Bigger number in the numerator gives us a bigger answer and therefore more electrostatic attraction, which would mean we need more energy to overcome that attraction. Thinking about the period trend right now. So hopefully that makes sense, but it may have also just made sense writing that. The reason why I wrote all this is for the group trend. What's happening as we go up a group? The valence electron that we're trying to remove is closer to the nucleus, right? As we go, as n increases down the group, we're getting farther away. So as n is decreasing, we can see that the ionization energy is increasing. But why? Distance is in the denominator. If we put a smaller value for r into an equation in our denominator, we're going to get a bigger answer. The closer two charges are to each other, the more attraction there is between those charges. I like to use, not really an analogy, a situation that affected students about, decade and a half ago. The bus system went on strike. And if you live on campus or close to campus, it didn't really affect you too much. But if you were relying on that bus, then that bus system going on strike really affected you. The closer these things are to each other, the more they're affected by each other. So distance made a difference on the impact to students on the bus strike. Distance makes a difference to electrostatic attraction as well. Any questions before we get a little bit more ionization energy? Make sure I've covered everything. We're going to now look at some actual data and notice trends are generalizations. There are always little blips in the radar, things that don't follow the trends. And although there are lots of them in this figure from our textbook, we're going to focus on two specifically. Now, these two elements are nitrogen and oxygen. Notice our atomic number for our x-axis is increasing. Nitrogen and oxygen is number 7 and number 8. Meaning for that tick mark 10 where the spike is, that's our neon. You can kind of count backwards. Neon, fluorine, then we have our oxygen, and the nitrogen is a little higher than it should be. And oxygen is a little lower than it should be. Let's see if we can understand why. So go ahead and bump everything up a little bit. We have this table to fill out, and I'd like to, where it says electron configuration, I've added the word atom, because students at times get confused as to what's the electron configuration of. So again, nitrogen is going to be there, oxygen is going to be over there. So for the electron configuration of the atoms, I'm going to do noble gas. So we have helium, 2s2, 2p3 for nitrogen. And for our oxygen, we have helium, 2s2, 2p4. Then we're going to think about the orbital diagram, and I'm only going to do it for the p sublevel just to keep things nice and neat. So for our nitrogen, we know that p has 3 orbitals in a sublevel. We have to make sure to label, otherwise we're losing some quantum numbers. We have 3 electrons, 1, 2, 3. In our oxygen, again, 3 orbitals. Label so we don't lose some quantum numbers. We have 4 electrons, Hund's rule. 1 per orbital, then pair up. We have 4. They ask us for the balance equation for the ionization energies just so we can understand what's happening. So for our nitrogen, we're going to N plus 1 electron. No, that is not the natural ion of nitrogen. We can do anything in the lab. We can take laser and blast electrons off of anions and make them the cations if we want. For our oxygen, that's going to O plus an electron. Again, not the natural ion we want to think of. What's the new orbital diagram for the +1 ion? Again, I'm only going to do the 2p. We lost an electron. For nitrogen, we've also lost an electron for oxygen. And if we go back to our graph, nitrogen was the one that way, those two dots, oxygen's the one to the right. Nitrogen's ionization energy is a little bit higher than you'd expect. If you wanted to make a straight line, one's higher, one's lower. That's why it's making it not be a straight line. Why is it a little higher? We're removing an electron from a half-filled P sublevel. Like half-filled Ds, half-filled P sublevels also give stability. Here we have a higher ionization energy than expected because it's trying so much to be neat. That's because my A got out of hand. Removing electron from half, get really close bottom, filled P sublevel. The D stability is getting greater, which is why I messed with our electron configurations. Remember again, D4, you take it to the S, you put it into the D to get that half filled. Well, oxygen's ionization energy is the one that's down. It's a little lower than expected because what's happening? We're going to a half-filled P. That means it kind of wants to lose this electron here because it wants this stability. So this one is lower than expected because getting to or going to I accidentally said D before P. You will be responsible for knowing the trend, but we gotta think outside the box sometimes and try to explain why sometimes things aren't perfectly following the trend. We can often investigate it this way. If we're thinking about removing electrons or adding electrons, then look at the electron configuration and what we're going from and what we're going to can help explain things. Plus you saw the half-filled and fully filled D idea. We know fully filled Ps are the noble gases, they're very stable. I wanted you to see also a half-filled P and what that does. Any questions? Yes?
Is that true for other sublevels as well, or is it just a T and P?
You don't see the same thing happening with S. Yes, filled is more stable, but you only have 2 electrons. But if I go back, oops, wrong way, we can see all kinds of weird stuff happening. That's actually in the transition metals, the 2 above my head right now, between potassium and krypton, rubium, and xenon. Over here where there's a dash line, that's like going through the past the intertransition metals. So yes, lots of weird things happen. At this level, you've seen the D thing, now you see the P thing. Depending on your major, you might investigate further in another class. It also is nice to show that trends are just generalizations. There's always little blips in the radar. Are there any questions? We're going to talk about one more topic. The fact that we can move more than 1 electron. So number 31, what is the difference between a first and a successive ionization energy? The one that we've been talking about so far is going from the atom to a +1 cation and removing 1 electron. That is technically the first ionization energy. But what if we wanted to go to a +2 cation? We would have to remove an electron from the +1. And that would require a different energy. Yes, it'd still be endothermic. If we wanted to go to a +3, we remove another electron. Another ionization energy would be incorporated. Each ionization energy is as you go through each step, the amount of energy needed is going to always be increasing. So the bottom of the slide, IE1 is always the easiest one. As we remove electrons, it becomes more difficult, needing more energy. The reason why the first one's the easiest one, we have electrostatic attraction between the electrons and the nucleus, right? But the atom itself is neutral. When we go to remove the second one, we have to overcome the attractive force of to further discuss this on Friday. I told you I didn't want to finish the trends today. There's more that goes into this. We're going to look at some specific. As you can see, there's a table, number 33, which is where we're going to be starting off. And then we'll finish